Hello people! In the previous video, we explored NumPy and its capabilities. Let us quickly recap what we learned before we head on to today's topic. We learned about n-dimensional arrays and their applications in numerical computing. Though NumPy is not often used in isolation, it is used under the hood by a lot of libraries like scikit-learn, pandas, TensorFlow, etc. NumPy is known for its speed and efficiency, which come from a couple properties called vectorization and broadcasting. Today, we are going to have a look at the Pandas library, its capabilities, and its applications. Pandas is short for Panel Datasets. Pandas is a powerful and widely used open-source Python library for data manipulation and analysis. Built on top of NumPy, it provides easy-to-use data structures and functions designed to work with structured data. At the core of Pandas are series and data frames. A series is a one-dimensional labeled array. A data frame is a two-dimensional data structure, similar to a table or a spreadsheet. Pandas provides data handling capabilities such as importing and exporting data from sources like CSV, Excel, SQL, JSON, and more. It is predominantly used to apply filters, transformations such as reshaping, aggregation, reshaping, etc., on the structured data. It has built-in time series and visualization support. Though the visualization capabilities are not comparable to dedicated tools like Tableau or Power BI, they are still adequate for preliminary data analysis, for most cases. Pandas is essential for data analysis, pre-processing, and cleaning tasks in data science, machine learning, and financial analytics. It simplifies working with large datasets and enables efficient exploratory data analysis, or EDA. Now that we know what Pandas is and what it is used for, let us head on to a more practical demonstration of its capabilities. Series and data frames are at the core of Pandas. Let us have a detailed look at these two data structures. A series is a one-dimensional labeled array, capable of holding any data type, such as integers, strings, floating point numbers, Python objects, etc. We create a series by calling the series function of Pandas. First, we import Pandas. The series function takes in data and an optional index. The axis labels are collectively referred to as the index. The length of the index should be the same as the length of the data. It is optional to provide the index. If the index is not provided, the default index is created. It is a sequence of whole numbers from 0 to n, where the upper bound is excluded. Notice the index is set to A, B, C in the first example, while in the second example, it is set to 0, 1, 2. The data can be a list, tuple, dictionary, ND array, etc. When it is a dictionary, the keys are set as the indices of the series. Just like an ND array, the series supports indexing, slicing, and vectorized operations. It has a single D type, an optional name. Once a series is created, it can function as a dictionary as well. A data frame is a two-dimensional labeled data structure, with columns of potentially different types. You can think of it like a spreadsheet, or SQL table, or a dictionary of series objects. It is generally the most commonly used Pandas object. Like series, data frame accepts many different kinds of inputs, like a dictionary of series, or lists, or ND arrays. Named tuples and structured arrays can also be used as inputs to create a data frame. In the first example, we attempt to create a data frame using a dictionary of two series. The first series, Carmakers, has the names of 3 carmakers, listed alphabetically. The second series has 4 superheroes, listed alphabetically. The two series have their respective indices passed. When we create a data frame using the dictionary D, the values get aligned neatly, with corresponding elements of the indices paired up. Since the Carmakers series does not have a value for the index D, a NaN value is set in its place. NaN stands for not a number. We can also pass the index, when creating the data frame object. This guarantees that only the indices present in the argument would appear on the data frame. Note that the index C is omitted in this case. We can obtain the list of indices and the list of column names from the index and column attributes of the data frame. There are a couple alternate ways of constructing a data frame: the from_dict and the from_records constructors. The from_dict constructor takes a dictionary of dictionaries, or a dictionary of array-like sequences, and returns a data frame. It operates like the data frame constructor, except for the orient parameter, which is columns by default. But when set to index, dictionary keys are used as row labels. The from_records constructor takes a list of tuples, or an ND array with structured D type. In this example, we use a two-dimensional NumPy array, created using a list of tuples. We can also specify the data types of the values, and set a specific column as the index. While NumPy stores strings in raw byte format, it is possible to make it store the strings in Unicode format by explicitly declaring the type as U. In real-world scenarios, data frames are the commonly used data structures. Each column of a data frame functions as a series. Alright, until now, we have talked about how we can create a data frame from scratch. But, more often than not, the data we need would be hosted on external sources, like CSV files, SQL tables, Parquet files, and so on. We would also be required to write the data to a file after processing. Let us see the options that Pandas gives us pertaining to data input and output. As we can see from the table, Pandas supports a lot of data formats. Reading and writing to CSV, XLSX, Feather, Parquet, etc. are supported. It is worth mentioning that there are a few formats for which there is only read support. All the read methods take in the file path as a parameter. There are some other arguments that modify the read behavior, like headers, delimiter, etc. Long story short, we have a handful of options to read the data from and write to, and we have considerable control over the read and write behavior. Here is how we read a CSV file. We pass the file path as an argument to the read_CSV function. Pandas does a good job of inferring the data type automatically, but in some cases, manual intervention may be required. In Pandas, both series and data frames support indexing and slicing. We can choose the items based on position or axis labels. This is made possible by the lock and iLock methods. It is possible to index or slice a single item or a chunk of the series or the data frame. Item assignment is also supported. In this example, we define a data frame containing the names of car makers and superheroes in an alphabetical order. Notice that the name of the car maker, starting with alphabet A, is Aston Martin, and that there is no car maker starting with the alphabet D. Here, we pick the name of the car maker starting with an A, using the two methods. In the lock method, we specify the names of the axis labels, A, and car maker. In the iLock method, we specify the index position. A is at index 0, and the column car maker is at index 0. In both the cases, the value is correctly returned as Aston Martin. We could also assign a value to a particular cell. In this example, we assign the value of Dodge to the carmaker series at index D, because it is currently a null value. We could use the same syntax and assign value to the cell. Notice that the value has been appropriately set in the original data frame. While indexing is picking a specific row, column, or cell, slicing refers to picking a chunk. Considering the previous data frame of car makers and superheroes, which is given on the right side, we are going to understand how slicing works. In this case, we choose all the data relating to the alphabet A. We can either provide the list of all columns as a list, as in line number 2, or a single colon, as in line number 3. The presence of the colon indicates that all the rows or columns are to be selected. We can also perform item assignments at a chunk level. Here, we set the values of superheroes column using the slicing syntax. In the row part of the lock method, we provide a colon, which means that the value is for all the rows. The column part of the lock method has a single column. So, in essence, we are saying that we want to assign values to all the elements of the superheroes column. We assign a list of 4 superheroes to the column. This has been updated correctly as expected. In Pandas, both join and merge are used to combine data frames. But they differ in syntax, flexibility, and typical use cases. Here is a breakdown of the key differences. Merge combines the data frames based on a column. If not specified, the common column is picked. Join usually combines the data frames on index, but it also supports a single column as the key. Merge supports multiple join keys, while join does not. Merge can handle logically similar columns with different names, but join cannot handle that. In summary, merge is more flexible and offers more control over the combining of data frames. Time for some examples. To demonstrate the differences between merging and joining, we are going to use 2 data frames, which are on the right. As we discussed, join combines the data frames by their indices. To account for common columns on the 2 data frames, we use left suffix and right suffix parameters. The left data frame contains information about cars, so we use _car as left suffix, and _hero as right suffix for similar reasons. If there are no common columns, these 2 parameters are not necessary. We can see that the data frames are joined on indices. 0th row of the first data frame is joined with the 0th row of the second data frame. But the join does not make sense logically, because the alphabets are not aligned. But there is a way to properly align the alphabets. If we set the alphabet column as the index of one of the data frames, the join operation would look for a matching column on the other data frame and join them accordingly. Now, we can see that the alphabets are properly aligned. The default join is the inner join, which can be overridden by using the parameter how. Merge is a more flexible and easy to understand operation. The simplest merge operation is demonstrated here. Even when we don't specify the column name, the common column is correctly picked. Also, note that the alphabets are properly aligned. Since an inner join is performed by default, only the matching values in the alphabets column appear in the result data frame. If we want to override the default join type, we can do so by using the how parameter. If the 2 data frames have a logically similar column, but they are differently named, we can use left_on and right_on parameters to specify the join keys. So, it is evident that merge gives us greater control over the combining operation. Using Pandas, we can concatenate 2 data frames. We can also compare the data contained in them and list down the differences. These 2 are very simple, but widely used operations. In this example, we create 2 data frames, Marvel and DC, which contain a list of superheroes in the respective universes. When creating the data frames, we have given a string as value to the universe column, while giving a list as value to the superheroes column. When one of the columns is a list, and the other is a constant value, the constant value is replicated to match the size of the list. Here, the strings Marvel and DC are replicated. Now, we concatenate these 2 data frames into one big data frame. By default, the data frames are stacked vertically. In other words, the axis parameter has a default value of 0. When the ignore_index parameter is set to true, the indices are rebuilt. If it is not set to true, the original indices are retained. This is an example of concatenating the data frames along axis 1. This is not a join operation. The data frames are just stacked horizontally in this case. More often than not, we might be required to compare the data in 2 data frames. It could be to track changes before and after an operation. Let us see how Pandas helps us with that. We use the data frame DC and create 2 copies of it. In one of the data frames, we modify a value. When we compare the 2 data frames, the differences are listed. Notice that the change from Cyborg to Green Lantern is captured. That brings us to the end of part 1 on Pandas. We learned about Pandas, its applications, and the core data structures like series and data frames. We had a brief glance at the data input and output, indexing, and slicing. We also delved into some operations on data frames, like merging, joining, concatenating, etc. In the next part, we'll explore further. For more tutorials, like, share, and subscribe. Don't forget to hit that bell icon. Until next time, happy learning!